chug. It's $19 and it's already set up with a 5-volt regulation system.
Okay, I'm gonna get started.
Go ahead.
Okay.
Educate.
So as most of you know, this is a presentation on solar power. This is a good introduction into the current solar technologies available, as well as the history and some of the emerging and future technologies that are coming about. So, if you look at the actual history of solar power, a lot of historians would probably say that it dates back to, 1600s, 1400s.
Plants.
Huh?
Plants themselves. So
Yeah, I mean, yeah, you could say it dates back to plants. There were actually like Chinese religious ceremonies where they would light fires with magnifying glasses. So that's typically declared as a historical event for solar power. But another thing that goes along with solar power is not just creating electricity from solar power, but also using thermal energy from solar power. So any type of means of using solar water heaters or some sort of means to keep your house warm, that's also included in solar energy. But I'm not really going to go over in that in this introduction. I'm kind of going more towards the electrical side of solar power. The first solar cell that was actually ever commercially invented and patented was here in the U.S. And that came about after a lot of research with different chemicals and materials like selenium, gallium, things like that. So we haven't really started to get good until actually developing a base with chemistry. And Albert Einstein actually published an article that, along with relativity, he published an article on the photoelectric effect. But you have to understand that photovoltaics haven't really started to come about until actually experimenting in the 1950s with different chemicals and understanding the periodic tables we know now. So if you look on here, you'll see that there's a couple different chemistries. You'll see, oops, okay, I did. So here, you'll see there's 5 different technologies. There's multi-junction cells, single junction, GAAS. There's crystalline SI cells. There's thin film technologies, and there's emerging EV. Now, the multi-junction are going to be more at the high end of what's currently available with photovoltaics. Single junction is basically, the best way to think about this is sort of like when, computers came out with single cores, and then they came out with triple cores, going like that. You basically have the same thing. You have single junction cells, and now you have triple junction cells. And basically, the more junctions that you add in, the more circuitry that you have available, and then hopefully the more current and more voltage you have available. But just pointing out right here, starting out in 1975, you can see that RCA started out with solar cells that were below, what is that, 5% efficiency? So 5% efficiency, that's nothing. That's basically, that means that the total amount of electricity, or the total amount of photonic energy that's hitting your surface, only 5% of it is actually being generated into electrical output. So if you're wasting 95% as heat that you're just not going to capture, it's just wasted. you can see that there's a little bit of this upturn, and then you have all these other companies come in. You have Kodak, Boeing, Monosolar, and then you have these other types of chemistries, like your thin film technologies, and that gets you up to about 15–17%. And right now, the most common type of solar cell that you're going to ever see is your crystalline cells, your silicon cells, and those are going to be your polycrystalline and your monocrystalline. So I'll go to the next slide. So
The other one was big.
I'll go back. So as far as your silicon-based cells, you have your mono, your poly, and then you also have your concentrated PV. And that's generally where you're going to see your multi-junction cells. CPV is basically like a very, very small, tiny cell that is going to have a concentrated lens over the top of it to concentrate all of that energy down to a very small space to hopefully disrupt or to release more electrons into your circuit. Agitate. Probably a good way of explaining this. We have markers, right?
Let's change the meaning of the group crystalline. Why is it there?
What is it?
There's an H in the word crystalline. Does that make it mean something other than what it sounds like?
Oh, crystalline.
Well, yeah, this is like a spelling error.
Is it a spelling error?
Or just fit that brick.
Or does that make the word mean something other than what I think? What do you mean? The H in the word crystalline.
You misspelled letter.
It is spelled crystalline.
I don't think I installed that.
Is there supposed to be an H there?
Yes.
Okay. Does it make it mean something other than single crystal?
I'm
No,
sorry, does
that's-
the word mean anything else to you without the H? I'm asking if that means anything else.
Googling.
Now, basically the way that every single solar cell is going to work, or most silicon-based solar cells, is you're going to have two ions that are doped inside of the silicon base. So basically, your silicon is just a dirt base. It does nothing in your solar cell except for being the structure that everything else is based on.
The medium?
Medium, yeah. So you basically have this really hard, rigid structure, and I've got a couple solar cells here that I can pass around.
Are they edible?
No.
Will they blend?
There actually are edible solar cells though.
Really?
Yes, there's organic solar cells.
I'm kind of hungry. I've got to decide between light and food.
So you
Well,
pick a
I mean,
leaf, eat it, you just ate a solar cell.
I don't know if they'd actually be edible, but they are organic.
Well, they're very different. That's
Yeah,
very different.
I know.
Poison ivy is organic.
You can still eat it.
Yeah,
Once again, plants.
yeah.
You can eat a window.
No H.
Now that we've established a spelling mistake,
So basically what you have
It is a spell. Okay, thank you. I feel better.
you basically have silicon, which is, it's sort of like sand. So you have a silicon base, and then you'll usually dope it with two chemicals. And that's usually phosphorus, which is a negative ion. Normally, I'm pretty sure it's a negative ion.
Yeah.
And then you usually have boron, which is usually the positive ion.
You say dope as a verb.
Yeah.
Like,
Elucidate on that, please.
No, this is the traditional terminology that they use. So CPUs and other electronics that are silicon-based, they dope them with chemicals to give them different properties.
So
So,
easy mix in.
right. So like transistors, they basically have silicon and then they dope it with some other chemical that allows it to be a semiconductor. Something that
Usually
that's-
involves very, microscopic scale, etching of the surface material, and then inlaying some other material to give it a property, and you're choosing the silicon as more of a surface structure for it.
So, if you look at this is like a printed circuit board, and basically you have this your silicon base, which is this sort of beige color, and then you have these copper connectors that are over it. So you can technically say that it's doped with copper. It's
It's basically a huge scale compared to what they would do on
Yeah.
something else like that.
But basically what happens is you'll have your two ions, and the way it is, I don't know what it would actually look like inside of your atoms and things like that, but the way that I think of it is basically like the electrons are basically leaning towards one ion, because you have this polarity where they're basically all leaning one direction. And then let's say that there's a photon that comes in like this, and then that's all you really need to push that electron off its orbital